When you get your file off of your Android device, you will now be able to process and work with your data that you've collected. When you open the file in Excel or any other spreadsheet type program, you'll see all the data that you collected. You'll notice that each of the different elements and topics are going across in the columns, and each of the different cycles that you measured are going down in the rows in the spreadsheet. In this case here, you can see that I have cycle 1, I have a time for felling, then these are my notes in text, my notes for numerical, then my second element, which is boom out, and then notes, boom in time, and on and on and on. So this is what I get right when I open up my file. You'll notice that there's a lot of NA or non-applicable cells, and those are ones that aren't going to help me much at all in my analysis. So one of the first things I'm going to do is get rid of all of those that are non-applicable or zeros or not going to be used in my analysis. So when I do that, I can highlight those and right-click and delete those cells or that column. And when I'm done with that, I'm going to end up with a sheet that looks like this. In that case, I just have the core sets of data that I need for my project. I have kept the text cycle comments. In this case, I have a broken tree on cycle 6. And on the numerical cycle comments, I have a tree number that is associated with the volumes that we'll talk about in a little while. So I kept all those. The next thing I want to do is do some basic statistics and understand what type of data I have and make sure that it all makes sense. So when I do that, I'm going to add in some additional column or rows here that calculate the sum, or just basically adding up every single one of the items above there. I'm going to look for the minimum number in each of my cycles there to see what the shortest one was, and the maximum cycle time. I'll then get my average cycle time and my median cycle time for that particular element. As I'm doing that, I can then drag that to the right in order to fill over to the right and do that for each of the different elements that we have here. With this, I can help look at the information that I have and try to make sure that everything makes sense and there isn't any real big outliers. If I had a number that was like 30 minutes in here and every other number is less than a minute, then that's going to tell me, hey, something's going on with that one, and I'm going to have to look and see what's going on there and see if I can figure out if that was me mistyping something as I was entering in the data, or was it something else that was going on and it really needs to be there. So with that, that's the basic statistics. The next thing I'm going to do is work on travel time here. And if you realize as you watch a harvester operate, sometimes that harvester has to drive and travel along the corridor to get to a next bunch of trees. It's not really fair to the trees that have to have that travel time associated with them, because it's not their fault for being that tree on that cycle. It's really just a nature of the way that the machine works. So as far as this in the harvester example here, what we're going to do is we're going to take that total amount of travel time, which is this 0.655 minutes, and we're going to basically distribute that out evenly amongst every tree or every cycle that we have, so all 10 cycles. So as I do that, I can come in here and I'm going to take this 0.655, I'm going to divide that by my total number of cycles, which is 10 in this case, and I'm going to put that value in this column for distributed travel time, and that is my now 0.655 minutes is now distributed equally amongst all of those. I can then calculate out my total cycle time by adding the felling, the boom out, the boom in, the processing, and the distributed travel time. when I sum those all together, those are going to give me the total cycle time for that first tree or that first cycle. Again, I'm not using the travel column here. I'm using the distributed travel instead. So I can do that for the first cycle, and I can fill that down in order to calculate out the cycle times for every single one of those cycles. This gives me the total amount of cycle time, and again, I can copy or fill over and figure out what the sum, the minimum, maximum, average, and median time is. So in this case here, my average time is just under 1 minute for a cycle to occur, and the shortest cycle was 0.76 minutes, and the longest cycle was 1.3 minutes. So the next thing I want to do is associate tree volumes with these cycles. I can do that by bringing in data from a survey that I've done of those trees beforehand, from inventory data, or other data sources that would have the volumes associated with each of those cycles. In this case here, I have diameter data and height data, and I have a volume equation to help me calculate out what that volume is. And when I do that, I get a volume for each one of those trees that were harvested in that cycle. The end result here is that I would like to find out what my productivity is. And I can do that by looking at my volume that I have and my cycle time and calculate out my productivity in cubic meters per hour. Now I can do that by taking the volume, so my cubic meters, and I'm going to divide that by my cycle time, which in this case is that 0.8695, and then I'm going to multiply that by 60, because that cycle time is in minutes, and if we want productivity in per hour, we have to multiply that by 60 minutes in order to get that into an hour format. And so when you do that, you get out productivity per hour in cubic meters. We can then again pull over our information from the bottom there, looking at the sum, min, max, average, and median there to come up with what we think is an average for that particular site. So in this case here, it's just about 20, just over 20 cubic meters per hour is the productivity of that John Deere on that site using those trees and with that operator. So 20 cubic meters per hour is what we would expect on that site. We can then go one step further and try to figure out how to use that information to predict or to better understand future activities where the conditions might be slightly different. In this case here, we can plot out our productivity, and maybe we can plot that out with our diameter of the tree so we can see how the diameter of the tree affects the productivity of the John Deere harvester. So in this case here, I plotted those out, and we're using what's called a scatter plot. This is not a line plot, but this is a scatter plot. And the scatter plot puts the diameter on the bottom here in dBH, and on the vertical axis, we have our cubic meters per hour. And what you see here is all of the dots from our data. These are, so we had a 15-inch tree here that had about 13.5 cubic meters per hour is one of our cycles. And then we had another one here that was 23 inches or centimeters in diameter, and it had almost a little over 21 cubic meters per hour. When all of those are plotted there, we can then identify what a trend line or an equation, a regression equation that will allow us to fit this line in here the most effectively to represent what the data is showing. We can do that by clicking on these. We right-click, and you can add a trend line. When you add a trend line, one of the options are to display equation on the chart, and display an R-squared value. And when you do that, you will get the equation right here for your line. What this equation is telling us is that the productivity, Y, is going to be based on 1.3706 times the diameter at breast height minus 9.258. And so that will tell you that if you're harvesting trees on the same sort of conditions that this data was coming from, if I'm harvesting only 22 centimeter trees, it's going to give me what that value would be right here on the plot, and it'll give you that exact productivity, and then we can use that to estimate out how long it might take us to harvest that particular site, what we might expect to harvest in a particular day, or how to maybe establish kind of a standard for what we would like our operators to aim for on any particular day. So the other key thing to look at here is the R-squared value. R-squared is a statistical term that helps us understand how well the line that we've established here, this regression line, how well that fits our data. And if that line, every dot that we collected was right on that line, that R-squared would equal 1. And if all the data that we collected looked like a shotgun blast and it was all over the place and there was no correlation or line, if you couldn't tell how any of those lines were, dots were related, that would be an R value closer to 0. So a perfect relationship would be 1, and absolutely no relationship would be at 0. 0.64 shows a bit of a relationship. It's not perfect, it's not fantastic, but it's not a bad relationship, and definitely shows, represents the data that we collected. So we can use these regression equations to help predict and set what's going to happen under situations with different diameters. We could also do regressions with other elements that we see from our data. So this is how to get started with analyzing your data. There's lots of different ways to do this. There's lots of statistics. You can get very deep into this, but this is the real basic component of it. We want to calculate out what our overall time is. We want to match that up with some sort of volume, in this case for our harvester, and then we want to calculate out what that productivity is. Once we know that productivity, we can then identify some regression equations that will help us predict what it's going to be at different scenarios or different conditions.